This lecture covers chapters 8 and 9. Do the Numbers Make Sense is chapter 9, and Measuring is chapter 8. Since chapter 9 goes so nicely with chapter 7, we're going to do chapter 9 first. This is called Do the Numbers Make Sense? We're only going to offer one example of checking whether the numbers make sense before we get to the topic that you can definitely be tested on for this chapter, which is percent change. Checking do the numbers make sense for this first example was already covered in chapter 7. Allergy relief medicine said they switched to a new formula maximum strength. However, the old formula had 37.5 milligrams of the active ingredient, and the new formula had only 25 milligrams. It turns out the FDA recently limited the dosage to 25 milligrams. The company complied and lowered its dosage, but called the new tablet maximum strength because it contained the federal maximum dosage. Always check that the numbers make sense. The one new item out of chapter 9 that we want you to know about is percent change. Why are we covering percent change in the Do the Numbers Make Sense chapter? Because percent change is often calculated and or reported incorrectly in the media. Let's study it and learn what it is. We have a formula, percent change equals the current minus the previous divided by the previous. This is when we're measuring this numerator, the current minus the previous, that's the new value minus the old value. This numerator is the amount of change over maybe a time period. In the denominator, you're measuring where you're dividing by where you started from. So you can either kind of think of current minus previous divided by previous, or new minus old divided by old. So the reason that we put the previous number in the denominator is because we want to measure the amount of change relative to where we started. When we measure the amount of change relative to where we started, this turns it into a percent. Relative means a fraction. A positive result in this calculation is read as a percent increase. A negative is read as a percent decrease. And once we get our number, don't forget to multiply by 100 up here to turn it into a percentage. Notice that we cannot have larger than 100% decrease. Mathematically, this is impossible, and also it doesn't make any sense. If I say I suffered a 50% decrease in my salary, we all know what that means. If I say that I have a 100% decrease, it basically means I got fired. I have no more salary. I took away all of it. If I say I had a 150% decrease in my salary, that's not possible. That means somebody took away more than all of my salary. Anyway, you can just memorize that you cannot have larger than 100% decrease. If anyone claims that they have any larger than 100% decrease, it makes no sense to think about it that way. Let's do an example. In 1987, the states spent collectively $10.6 billion on corrections. In 2008, they spent $44 billion. Calculate the percent change from 1987 to 2008. So our formula is current minus previous divided by previous. What's the newer number? In 2008, we spent $44 billion. The older number, previously, we spent $10.6. And what are we measuring it relative to? Relative to where we started. So that would be the previous number, 10.6. 44 minus 10.6 is 33.4. So the change in the amount we spent on corrections was $33.4 billion. But remember, we want to calculate it relative to where we started because we're computing percent change. So the amount that we spent extra was $33.4 billion. But we want to measure it relative to 10.6, where we started. And when we punch that in the calculator, we get 3.15. Now, a lot of you will stop here, and you'll say there was a 3.15% increase, because we got a positive number. We didn't get a negative number out of this one. However, that's not correct. Remember that we have to multiply by 100 at the end to turn it into a percentage. So this is actually a 315% increase. You can have higher than 100% increase. You just cannot have higher than 100% decrease. What does a 315% increase mean? Let's round that down to 300% for now so we can think about it in whole numbers for a moment. If I increase my original amount 100%, I've doubled my original amount. If I increase my original amount 200%, I've actually tripled the original amount. If I increase my original amount 300%, I've quadrupled my original amount. This makes sense for our example. 10.6 we could round to 11, and 44 is about 4 times the original amount. So this would equate to roughly a 300% increase. That's a good way to check your calculations. Now we get into the measurement portion of our lecture. This is covering Chapter 8. We measure a property of a person or thing when we assign a number to represent the property. We often use an instrument to make a measurement. We may have a choice of the units we use to record the measurements. The results of a measurement is a numerical variable that takes different values for people or things that differ in whatever we're measuring. Notice this is not a new definition of the word variable. We had a previous definition that said it was any characteristic of an individual. The results of a measurement are a specific type of variable, a numerical variable. Think about when you're measuring the length of something with a tape measure. You get a numerical outcome for that. So the results of measurements are a special type of variable, a numerical variable. Measuring length with a tape measure is concrete and precisely defined. Measuring other variables is not so clear-cut. Think about measuring college readiness. The admissions department at universities are tasked with measuring college readiness. This is how they make decisions on who to send acceptance letters to. This is not very clear-cut and easy to decide. How about fatalities from a car accident? At first glance, this might seem very concrete. However, we need to have some long, frank discussions on how to measure that variable. Do we say a fatality from a car accident are people who die at the scene, or people also who die later from injuries, or people who die later from complications from their injuries? How can you define variables then? They're not always clear-cut. Some questions you should ask: exactly how is the variable defined? Create a good working definition of your variable. 2. Is the variable a valid way to describe the property of interest? We're going to formally define valid in a minute, but it means exactly what it does in the regular English language. Is it an appropriate way to describe that property of interest? 3. How accurate are the measurements? For instance, the Bureau of Labor Statistics reports unemployment every month. But people who are not available for work are not counted. The people that we call not available for work are retirees, students, stay-at-home moms, etc. Being unemployed requires that first the person must be in the labor force. And second, the person must be available for work and looking for work. So if you're on strike but expected to return, you are considered employed. If you're not working and haven't looked for work for 2 weeks, you aren't in the labor force anymore. This one should send some red flags up for you. if you know a family member who is unemployed right now, if they haven't looked for work for 2 weeks, if they're just kind of waiting for those resumes to hit and get some calls back, and they get pulled in the unemployment numbers, they're not going to be even considered in the workforce, in the labor force. They're not going to be counted when we measure unemployment. You should check out our actual numbers for South Carolina, because when we report our unemployment numbers, lots of times these are really masking a larger problem that our labor force is actually shrinking. Anyway, it's hard to measure some variables. You need to pay close attention and be very careful in your definitions. Here comes our very important definition of the word valid. Always come back to this definition if you're ever struggling with a question on validity. A variable is a valid measure of a property if it is relevant or appropriate as a representation of that property. Clearly, we don't want to use someone's height as a measurement for their weight, right? We all understand that's not appropriate. It's not a good representation of weight. When we speak of validity in practice, it usually comes up in educational and psychological testing. For instance, if your teacher marks off for grammar on a science test, so your grade actually reflects both your science knowledge and your grammar knowledge, or your punctuation or whatever, then that is not a valid way to measure science ability. So validity often is called into question in educational and psychological testing when we're measuring latent variables. Often a rate, which is a fraction or percentage at which something occurs, is a more valid measure than a simple count of occurrences. For example, if we use a count for highway deaths and notice an increase from year to year, we would report that deaths have increased. So it would appear that highways are more unsafe. The Fatal Accident Reporting System reported 40,716 deaths in 1994 and 42,642 deaths in 2006. So it looks like the number of fatalities have gone up, which makes it look like the highways might be more unsafe. However, the number of licensed drivers increased from approximately 160 million to 203 million. More people drive more miles. So there could be more deaths even if the roads are safer. Count is not a valid measure of highway safety then. Rather than a count, we could use a rate like the number of deaths per driven mile. We've just discussed the definition of valid. Now let's talk about predictive validity. A measurement of a property has predictive validity if it can be used to predict success on tasks that are related to the property measured. For example, do SAT scores have predictive validity? What do we use SAT scores for? Well, SAT scores are used as a part of the criteria for your admittance to a university. The university hopes that SAT scores do have predictive validity. Is there a lot of variability in these predictions? Yes. Clearly, if you speak to anyone about their SAT score, usually they're going to say they don't think it accurately reflects what they can do. Many students say that. So, even though it's a heated issue, it still does have some predictive validity, and it's still used, but only as a portion of your admissions packet. Now let's talk about accuracy of measurements. Let's think about your bathroom scale. If your scale weighs 3 pounds too high, then the measurement that it gives you is your true weight plus 3 pounds. Now suppose that your scale reads 3 pounds too high because its aim is off. We're thinking about the old-fashioned kind of scale where a hand moves around a face, much like an old clock. So it adds 3 pounds, but this morning it sticks and weighs you 1/2 pound lighter. Then the measurement that it gives you is the true weight plus the 3 pounds minus a half of a pound. So, ladies, I'm sure you can identify here. You jump off and back on the scale to see that half of a pound weight loss, but this time it sticks to add a quarter of a pound. Then the measurement it gave you is your true weight plus the 3 pounds plus a quarter of a pound. So this bathroom scale then has two types of errors. It's got this error that's always adding 3 pounds, and then it's got the other error which seems unpredictable. Sometimes it's taking off a half of a pound, sometimes it's adding a quarter of a pound. Those are two different types of errors. The first one is called bias. This is that third time in the semester that we told you the word bias would come up. Again, it means the same thing, off in the same direction every time. This scale is biased by adding 3 pounds to every measurement. This is a systematic error that occurs every time. So a measurement process has bias if it systematically overstates or understates the true value of the property that it measures. The other type of error, which doesn't seem to be predictable, is called random error. A measurement process has random error if repeated measurements on the same individual give different results. So remember, we can determine random error by looking at repeated measurements on the same individual. If random error is small, we say that the measurement is reliable. So some big terms here that are going to come up are bias and reliability. Bias is that repeated deviation in the same direction. It's predictable, but it's still a type of error. And reliability is about how big or small your random error is. It's not predictable, and it's a different type of error. We can think about errors in measurement in the following way. The measurement that you get from whatever measuring process you're using is going to be the true amount plus any bias plus any random error. Now, of course, we want a measuring process that minimizes bias and random error at the same time. Bias is easy to correct for once you know it's there. You could just subtract that amount back off. But random error is a little tougher. What do we do about random error? It's not predictable. Remember that reliability says that the result is repeatable, meaning we can get the same thing each time we measure somebody. So how are we going to handle it when we don't have reliability? That is, when the random error is large. Well, one strategy that we have is to use the average of several repeated measurements on the same individual. This is going to be more reliable. So use averages to improve reliability. Think about it. If a scale is adding a little bit here, subtracting a little bit on this measurement, hopefully those will cancel each other out when we take the average. So remember that we can use averages to improve reliability.